Hello students, we are dealing with unit number 2, that is inverse Laplace transform, and in this method we are dealing with the different methods to find the inverse Laplace transform. So far we have studied 4 methods to find inverse Laplace transform. The methods are use of standard results, use of shifting theorem, use of method of partial fraction, and use of differentiation of f bar of s. Now the next method is use of integration of f of t. We will see its procedure. Use of integration of f of t. By Laplace transform of integral we have, if L of f of t is equal to f bar of s, then L of integration of 0 to t f of t dt is equal to 1 upon s f bar of s. It means that if there is 1 upon s multiplier in f bar of s or in the Laplace transform result of a function, then there should be integration from 0 to t in the f of t. So if we are having 1 upon s, 1 upon s square, 1 upon s cube terms in the function of s, then there should be those number of integrations in f of t. So taking inverse Laplace transform on both the sides of this result, we get integration from 0 to t f of t dt is equal to L inverse of 1 upon s f bar of s. If it is 1 upon s square, then there should be one more integration. If it is one more s, that is if it is s 1 upon s cube, then there should be 3 integrations from 0 to t. So remember this one, the number of multipliers 1 upon s indicates the number of integrations in the required f of t. So using this one we can write, if L inverse of f bar of s, this result is obtained using this one. If L inverse of f bar of s is f of t, then L inverse of 1 upon s f bar of s is integration from 0 to t f of t dt. So now we will see its procedure in short. So in the given function of s, first you have to identify f bar of s, means other than 1 upon s, 1 upon s square, 1 upon s cube terms, whatever is the function of s is there, you have to take it as f bar of s. Then take its inverse Laplace transform, or you can say you can find its inverse Laplace transform using the previously studied methods. That is, it may require use of standard results, it may require use of shifting theorem, it may be calculated using method of partial fraction or the method of differentiation of f bar of s. Then you will get f of t. And the last step is very important, that is you have to take integration of this latest result f of t in the interval 0 to t. So if there is 1 upon s, you have to take integration only once. If there is 1 upon s square, you have to integrate the function f of t 2 times. If it is 1 upon s cube, you have to integrate f of t 3 times. So we will see all these things in examples. Question will be same. Find the inverse Laplace transform of. Now first example, 1 upon s into s square plus 4. See, this function can be written as 1 upon s into bracket 1 upon s square plus 4. So surely this square bracket term 1 upon s square plus 4 is your f bar of s. So this is the first step to identify f bar of s. So here 1 upon, without 1 upon s, whatever the function is there, you have to take it as f bar of s, and here it is 1 upon s square plus 4. Now using the method of standard results, you can find inverse LT of this f bar of s. So taking inverse Laplace transform on both the sides, we get L inverse f bar of s is equal to L inverse 1 upon S square plus 4. Use of standard result method gives answer as 1 by 2 sine 2t. So this is our f of t. Whatever is f bar of s we have considered, its inverse LT is our f of t. So this is our second step in the procedure. Now the last step, that is to integrate this f of t within the limits 0 to t. So you have to write here result. If L inverse f bar of s is equal to f of t, then L inverse 1 upon s f bar of s is equal to integration from 0 to t f of t dt. So you have to integrate this f of t within the limits 0 to t. And here you can write L inverse of the original given function with 1 upon s as a multiplier. So 1 upon s indicates only one integration. So it is 0 to t f of t dt. Here f of t is 1 by 2 sine 2t. Now by linearity property of integrals, we can write this constant multiplier out of the integration sign. So it becomes 1 by 2 integration from 0 to t sine 2t dt. Now here we have to use the formulae to find the integration. Integration of sine theta is minus cos theta divided by derivative of theta. Here theta is equal to 2t. So the answer is 1 by 2 is a multiplier as it is. Integration of sine 2t is minus cos 2t divided by derivative of 2t, that is 2, within the limits 0 to 2. Now here the complete constant multiplier is minus 1 by 4. 1 by 2 out of the bracket and minus 1 by 2 inside the bracket. So total constant multiplier is minus 1 by 4. So this we can write minus 1 by 4, and you can put the limits only for the function cos 2t, upper limit t and lower limit 0. So it becomes minus 1 by 4 cos 2t minus cos 0. So we know that cos 0 is 1. So it is minus 1 by 4 cos 2t minus 1. Now taking this minus sign inside this bracket, we get the final answer as 1 by 4 into bracket 1 minus cos 2t. Remember, this is not the final answer, but it is the intermediate answer, and this is the final answer which we have obtained after taking integration once, and that is with respect to t. So this is our final answer. We will see one more example. Now here we are having 1 upon s square into s plus 1. We can write this as 1 upon s square into bracket 1 upon s plus 1. So this square bracket function 1 upon s plus 1 is your f bar of s, and since here 1 upon s is appearing 2 times, means we have to take integration of f of t 2 times. Remember this one, otherwise you will lose marks. So our first step to identify f bar of s, here in this example it is 1 upon s plus 1. So f bar of s is equal to 1 upon s plus 1. Again, using the method of use of standard results, you can find its inverse LT, and it is very simple. It is equal to e raised to minus t. So this is your f of t. This is your intermediate function of t and not the final answer. Now we will take the 1 upon s factors in this given function one by one. So first e raised to minus t as the result for f of t. Using this L inverse f bar of s is equal to f of t, then L inverse 1 upon s f bar of s is equal to integration 0 to t f of t dt. We can write L inverse 1 upon s into s plus 1. Remember, here we have taken only 1 upon s and not 1 upon s square. We are going to take 1 upon s as a multiplier 1 by 1. So here we have to integrate this f of t, which is e raised to minus t. We are having the result of integration e raised to ax dx as e raised to ax upon a. So using that result, we get integration as minus e raised to minus t within the limit 0 to t. Again here, using linearity property, we can write minus sign outside the curly bracket. So it is e raised to minus t, that is lower limit value, minus e raised to 0, that is e raised to minus t is upper limit value and e raised to 0 is lower limit value. Now again, after multiplying by this minus 1 inside the bracket, we get it as 1 minus e raised to minus t. See, again this is not the final answer, because we have to consider one more 1 upon s, means we have to integrate one more time. So this is again one more intermediate function, and as already we have used f of t, here I am using another letter g of t. So to get the final answer, we have to integrate this g of t with respect to t within the limits 0 to t. So that result will be for the required function result, that is L inverse of 1 upon s square into s plus 1, that is integration 0 to t. This latest result g of t you have to consider for integration, and it is 1 minus e raised to minus t. Integration of 1 with respect to t is t. Integration of e raised to minus t is e raised to minus t upon minus 1. This minus sign and minus divisor gives you plus in between t and e raised to minus t. Then put lower limit and upper limit. For upper limit, we get the term as it is, t plus e raised to minus t, minus lower limit terms 0 plus e raised to 0, that is 1. So on simplification, we get t plus e raised to minus t minus 1 as the final answer. If the original function is having 1 upon s cube, in that case you have to treat this function as some h of t, and you have to integrate one more time this h of t, so that you will get the final answer. So number of 1 upon s factors in the given function decides the number of integrations with respect to t within the limit 0 to t. So in this way you can use this method, that is use of integration of f of t, to find inverse Laplace transform of the given function of s. So some examples for practice. Question is as it is, find the inverse LT of. This example is very similar to the first example which we have solved. So 1 upon s indicates only one time integration, and f bar of s is 1 upon s square plus 9. You can find its inverse LT using the first method, that is use of standard results. So this is very simple example. Second example, it is very similar to the second example solved one. Here f bar of s is 1 upon s plus 2. Again its inverse LT can be found out using the use of standard result method, but this 1 upon s plus 2 is multiplied by 1 upon s square, that is 1 upon s 2 times, means you have to integrate f of t 2 times. So remember this thing, the number of 1 upon s factors in the given function decides the number of integrations with respect to t. One more example, 1 upon s log of s square plus a square upon s square plus b square. It is very clear that f bar of s is log of s square plus a square upon s square plus b square. Now to find its inverse LT, you have to use differentiation of f bar of s method, because log, tan inverse, cot inverse, such kind of functions can be solved using the differentiation of f bar of s method only. So you have to first find inverse LT of this log of s square plus a square upon s square plus b square using that method, then apply 1 upon s factor, so that you will integrate the latest f of t within the limit 0 to t, and check whether you are getting this answer or not. This method is also very useful to find inverse LT of the functions. Such type of examples may be asked in MCQs. So this method is not having that much weightage in university question paper examples, but it may be used in another method, that is use of convolution theorem or use of method of partial fraction, or sometimes with another method in combination. It may be required in, or we can say it is also useful in the applications of Laplace transform to solve simultaneous linear differential equations, or just to get the solution of linear differential equations with the constant coefficient. So solve these examples and check whether you are getting the same answers or not. Thank you.